Okay, so let's get started. So now we're going to be talking about, so we're not going to be talking about graphs, and well, we'll still be talking about graphs, but we're kind of done with flow and shortest paths and all that. Now we're going to kind of be talking about a meta topic. And the reason I say meta is like, we're not going to be thinking about one problem. We're actually going to be thinking about classes of problems, okay? So essentially the goal is we're going to try to see what makes a problem easy or what makes a problem hard, right? So it's kind of like we're going to be doing a slightly meta reasoning. And yeah, so today I'm going to introduce lots of new definitions. So like if you don't understand a definition, please ask. Otherwise, you're going to be lost, right? So today's the time to ask, new definition. If it doesn't make sense, right? Please ask. Okay. And essentially, like, yeah, like the goal is to say, okay, what makes a algorithms problem, like shortest paths in polynomial time, versus another problem, like if I say find the longest path between two nodes, that actually turns out there's no polynomial time, or no known polynomial time the algorithm, and people suspect there's no polynomial time algorithm. Like, what makes those two problems different from each other? Or like, right, I say sorting, right? We can sort in polynomial time, but if I say here's just like another random problem that's much harder, which is, right, if you heard about the traveling salesperson problem, right, if I give you a bunch of cities on a map and cities and distances between them, and I say find a path that visits all the cities of the smallest cost, total cost, turns out there's no known polynomial time algorithm to solve that problem. So, right, so this, I'm going to be introducing some ways to kind of think about, right, what makes a problem easy versus hard. And when I say easy, I really mean like, we can actually write a polynomial time algorithm versus there's no polynomial time algorithm. Maybe kind of the best known algorithm is to do some like brute force search, okay? All right, so that's what the class is going to be about. So to make things a little bit simpler, we're not going to be looking at like general problems. We're going to be looking at like a simplified version called decision problems. So these are just problems where the answer is a yes or no, okay? So if I give you n numbers and I say, is this list sorted or not? Yes or no, okay? For instance, right, you can say, okay, let's say for shortest paths, right? Previously I said shortest path is find the shortest paths, but you can turn it into a yes or no problem by saying, if I give two vertices, is there a path of length at most 100, okay? So that's a yes or no question. So it's, so today we're going to be looking at, or actually for the next 2 weeks, we're just going to be looking at yes or no problems, okay? So the answer is not a number. It's just going to be yes or no. All right? So if I give you an input, like let's say if I give you a graph, is the graph connected, yes or no? Or does it exist a minimum spanning tree of cost at most 5,000, okay? Yes or no, okay? That's a yes or no question. And in general, like this is not like a restriction. Actually, we can turn any of the problems that we've studied into yes or no questions, right? Like if I say, okay, what is the shortest path between S and T? Well, I can turn it into a bunch of yes or no questions by doing binary search on the value, okay? Like, does there exist a path of length 10 or 20 or 50 and so on? All right, so, but yeah, for the rest of this class and for a few more classes, right, we're going to look at these problems called decision problems, and they're yes or no. And now what we're trying to do is we're going to say, okay, if I give you a decision problem, right? So previously we fixed a problem and we say, if I give you an input, how do I solve the input on that problem? Now it's a little bit like more meta thinking, okay? If I give you a problem itself, how do I know if that problem is easy? Meaning, can I solve, there exists some polynomial time algorithm versus hard, which is probably there's no polynomial time algorithm, okay? But here, these are some examples of yes or no problems, okay? Decision problems. Like for instance, right, if I give you an array, right, is the array sorted? Yes or no? Or if I give you a graph, I can say, does there exist a path from S to T with total weight at most some value? Okay, that's a yes or no question. Or even like chess, right? I give you a configuration of the board, and I say, can player one win, starting from this board? Or Tetris game, right? I give you a starting configuration of Tetris and a sequence of pieces that will come, and I say, can you survive this game, right? That's a yes or no question. Yeah, does that make sense? What is a decision problem? right? We're just trying to just decide yes or no, okay? All right? Okay, so now I'm going to introduce sort of, so this is a class of problems, okay? It's called P. It's sort of like a meta classification, okay? It's like, it's not about a particular graph. It's about like a description of the problem itself, okay? So I say a problem is in P if there exists a polynomial time algorithm for it, okay? So what does that mean, right? If I give you an input of size n, for instance, a graph with like, n square edges, then there's a polynomial time algorithm to solve the problem, okay? So far, like, everything we've looked at has been, or most of the things we looked at has been in polynomial time, right? Like max flow is in polynomial time, shortest path is in polynomial time, sorting, all these greedy algorithms, minimum spanning tree, right? They've all been in polynomial time, okay? And right, for when we make this classification, we don't care like how fast or slow the polynomial is. We're just trying to, at the heart of it, we're just trying to like distinguish between problems that require polynomial time versus those that maybe require exponential time, okay? That's essentially where we're getting at. Okay? So the class P is this class of problems. It's just a set of all problems that have polynomial time algorithms, okay? Does that make sense? This is the class P, okay? All right. Yeah, so I'm not going to be super formal about what an algorithm is, but just imagine, right, like the number of steps you take is polynomial, okay? All right. And like I said, like pretty much any reasonable problem that you've seen has been in class P, okay? Right. Okay. So now we have to, so now you might say, okay, then I have to like define some, the complement, like, but it's actually not so, it's not exactly that. So the next few definitions are going to be a little bit strange, but then we'll see, okay, like why exactly it's written that way, okay? But for now, does the class P make sense? It's just a classification of problems, okay? So some problems are not in P, okay? So if I tell you, I give you n numbers, write down all the permutations, right? That clearly takes n factorial time. It's not going to be in class P, okay? For example, okay? All right. All right. And now I'm going to define this other class. It's not exactly the opposite of P. It's a little bit different. It's a little bit a stranger object, but we're going to dive a little bit deeper, okay? It's called the class NP. And N doesn't stand for, and P doesn't stand for, okay. And the class NP doesn't really stand for not polynomial, okay? So that's false. But you can kind of think of it similar to that, okay? But it doesn't stand for not polynomial, okay? So if, it stands for some like weird terminology, non-deterministic polynomial time. We're not gonna care what that is. I'll give you like a different definition of NP that's more intuitive, okay? All right. So essentially, NP is a class of problems where I can verify the solution in polynomial time, okay? That's what NP is. That's what this non-deterministic part stands for. It's some fancy terminology about verification. But essentially, you can think of it's like, it's a class of problems where if I tell you a potential solution, I can verify it. So more precisely, right, a problem is in this class NP if there exists an algorithm, which if it's a yes instance says yes, no instance says no, but the algorithm has help, okay? So I'm going to help the algorithm. And the way I'm going to help the algorithm is I'm going to give it a hint. Call it x, okay? So I'll give you a specific example in a bit. But you can kind of think, or like, you don't really care how I came up with x, okay? It's just that there exists some help that I can give the algorithm that can help it correctly decide whether an input is a yes instance or an input is a no instance, okay? All right. So intuitively, you can think of the class NP as problems whose solution is easy to verify, okay? So what does that easy to verify mean, right? It says there exists a verifier called V, right, which is another algorithm that, right, if this x wasn't there, it'll just be a normal algorithm, right, that solves the problem, right? It says yes or no. But I give the algorithm slightly more power by saying I get to give it any hint I want, okay? So there's always going to be a hint that I can give the algorithm that helps it decide yes or no for an instance, okay? Right? But like I said, we're not talking about a specific problem, right? We're doing this meta thinking where we're thinking about the problem itself, right? And I'll give you some examples, but at least does the definition make sense? And if not, like, this is a good time to ask. Okay. Yeah. If you don't understand this, like, this is probably you should ask. Okay. So P is a class of problems which are easy to solve, right? There's a polynomial time algorithm. And P is a class of problems where I can verify the solution. Okay. So essentially, we'll see an example, but the hint X will be like, oh, here's a potential solution, and then V will just like check if the solution is correct. Okay. All right. Another way to think of this hint X is something called a certificate. It's like if this input I is a yes instance to the problem, there's going to be a one-way, like kind of a gold standard that or like some proof that I can provide to the verifier. And the verifier will check the proof and say, oh, okay, actually, this input is a yes instance. If the input is a no instance, there's going to be no way for me to provide this X, okay? All right, so we'll see a concrete example in a bit, but okay, so recall, right? These are some examples of decision problems, okay? So for instance, let's take a problem like chess, right? I give you a board and I say, okay, player 1 goes, can player 1 win from this position, okay? That's a hard problem to solve, right? Like, I have no idea. I mean, I don't know, but it is an easy problem to verify, okay? Why? Well, the X, the proof or the certificate, right, or the hint that I can give is, I can say, okay, these are the sequence of moves that you'll make. Okay, so actually, here's a different example. Tetris, okay? Tetris, right? I give you a, starting configuration, and I say, these are the pieces that will come. And I'll say, can you like survive this game, right? I mean, I don't know, right? There's so many choices, right? When a piece comes, so many choices of where to move it. But this X that I can give you is just say, okay, if I place it this piece here, this piece there, this piece there, then my claim is that then you can survive. That's very easy to check. Okay. So another example, right? Negative cycle, let's say. Does the graph have a negative cycle, yes or no? It's maybe hard to find, right? If I didn't tell you about this Bellman-Ford algorithm, you might not know. But this is a very easy problem to verify. I just tell you what the cycle is, okay? So if I tell you what the cycle is, then of course you can just check, right? I can just add the edge weights on the cycle, check if it's negative or not. And like conversely, right, if the graph doesn't have a negative weight cycle, right, there's going to be no such X that I can provide to the verifier, okay? Right, so for instance, in this example, right, consider the problem is, right, Q, the problem is, does the graph have a negative weight cycle, right? And the input I is a graph, right? I want to say yes or no. And now the verifier, right, is just gets a hint. And the hint will just be, here's an example, here's the negative weight cycle in the graph, okay? And now if I tell the verifier that, then it runs in polynomial time, right? I just check the edges on the claimed cycle of X, okay? And look, and correspondingly, right, if there is no negative weight cycle, then of course there's no way for me to come up with the claimed cycle, right? That's negative weight, okay? Okay, at least in the negative cycle case, does that make sense? Like why this is an easy problem to verify? If I just tell you what the proposed negative weight cycle is, I can just check, okay, in polynomial time. Finding it might be much harder, but a problem is in NP. I'm not asking you to find it. I'm just asking you to check something, okay? All right. Okay. Let's take another example, right? Let's consider the problem called subset sum, okay, which is I give you a list of numbers and a sum like 5, and I say, does there exist a subset of these numbers that add to that value 5? Okay, is it yes or no? Finding the subset, it actually turns out to be a hard problem, as we'll see next time. But this problem is an NP because checking it is very easy. If I just tell you what the subset is, then checking if that subset equals the sum is very easy, right? This is polynomial time. Okay. All right. So NP, like you can, like I said, you can think of it's a class of problems where if I provide a hint to some algorithm, it's very easy to check if it's a yes instance or a no instance. All right. Yeah. Okay. Let's just do one more example, right? Consider the problem called longest path. Okay. So the problem is I give you a parameter d, and I say, does the graph contain a simple path of length at least d? Okay. That's the problem. Yes or no? And here's I don't know. I actually never told you how to find long paths. It turns out to be a hard problem, but it's a very easy problem to check, right? So what is the certificate? Well, I can just tell you what the path is, right? If there's a super long path, then of course there always will exist a certificate. If there's no such path, right, then no certificate like that exists. So if I just tell you what the proposed path is, you can just easily check and verify that I was telling the truth. Okay. All right. Does this make sense? Like I said, P is a set of problems that are easy to solve, and P is a set of problems that are easy to verify. Okay. As we'll see, like checking if a problem is in P is actually hard because I have to come up with the algorithm. Like 99% of the time, checking if a problem is in NP is super easy. I just say, oh, imagine I told you the optimal solution. Can I check if it's correct? Okay, in polynomial time. Okay, so it turns out like most of the things we'll see, actually all the things we'll see in the class, checking if a problem is in NP is super easy. Okay, I just say, imagine the hint or the certificate the verifier is getting is the claimed optimal solution. Can I check that in polynomial time? That's all NP is asking you to do. Okay. Okay, so now I have these two classes of problems, right? P is a set of problems intuitively that are easy to solve, and P is a set of problems that are easy to verify. Can someone tell me why every problem that's in P is also in NP? Right, so if a problem is easy to solve, like there's a polynomial time algorithm, why does it mean that I can also, why does it mean that, right? What is the definition of NP, right? There exists a verifier. What is the verifier? Let's say Q is a problem in P also, right? So what can the verify, right? I know the problem is in P, so I know there exists some algorithm for it. Okay, how can I use that to create? I don't know what the algorithm is, right? I just know there exists because it's in P. How can I use that to create a way to like verify? Well, in some sense, it's sorry. Were you? Yeah. So it's essentially that's the right idea, right? The V, the verifier algorithm, will just be the algorithm that exists, and the X, it just won't even look at the certificate, right? It will just solve the problem exactly, right? And then decide yes or no, okay? Right? Because it's in P, there is a polynomial time algorithm, right? I can let V be that algorithm. What it does is, well, it doesn't even look at any certificate. Let's say the certificate is just a blank number, right? Blank certificate. What it does is it like directly solves the problem and checks if it's yes or no, okay? All right. All right. So, and that intuitively makes sense, right? Any problem that's easy to solve is also easy to verify. What do? I just solve the problem, okay? And then then because I've solved it, of course I know whether it's a yes or no, okay? All right. Like I said, the verifier just solves the instance and just ignores whatever you give it as the certificate, right? Because we know there's a polynomial time algorithm. Of course, I know exactly whether it's yes or no. Okay. So right. So one trick is right. Whenever we think about problems in P or NP, you can just like pretend you have the verifier in the NP case, or if I know a problem is in P, I can pretend I have the algorithm at hand, right? Because I'm telling you it's in P, right? There must be an algorithm for it. Okay. All right. So the big, well, I guess one of the big open problems in computer science is, does P equal NP? So what that means is, right, P is a set of problems that are easy to solve. NP is potentially a much bigger set, okay? It's a much bigger set of problems that are easy to verify. And the question essentially is, if I take a problem that's easy to verify, meaning, right, there is an algorithm such that if I provided a hint, it can check yes or no, can I actually solve the problem without a hint? Okay, so that's the P versus NP question. Yeah, it's like a very fundamental question, right? Nobody knows. I mean, we think, right? People think P is not equal to NP, right? Internally, right? Like checking is a much easier task. That's why NP is a much bigger class of problems, right? Hopefully, because checking something is much easier than solving something. But actually, it's not known, right? We don't have a candidate problem that says, oh, for this problem, right, there's no polynomial time the algorithm, but if I tell you a certificate or hint, I can check it in polynomial time. We don't know if such a problem exists. Okay, so that's why it's a big open question. Yeah. Okay, so right. Okay, so so far, I've defined these two classes, P and NP. Does that make sense? If it doesn't make sense, this is the right time to ask. Because now I'm going to define more, like 2 more classes, okay, after this. Okay. Yeah.
What you were saying about P equaling NP, the verifying part, is it just for one problem, like every specific problem, or is it for each, like all of them together? What exactly?
Yeah, so it's like a problem-specific thing. So I'm saying, so right, when I say P equals NP, right, P is a set, right? It's a set of problems. NP is another set of problems. What I want to say is every problem in NP also in the set P, right? So why is a problem in NP, right? If I tell you a problem is in NP, it means there is a verifier for that problem, right? It could be different for different problems. But for that specific problem, there's a way for me to check the answer, right? So imagine the Tetris case, right? How do you check it in polynomial time? If someone tells you the moves to make, like you put this piece here, put this here, just like follow the moves, right? It's super easy to check, right? So that's why this problem is in NP. But I'm saying, is the problem also in P? Well, for it to be in P, I actually need to come up with the sequence of moves, right? Nobody tells me what they are. So, so asking if a problem is in P is a much harder question because I need to come up with a clever way to solve the problem. Asking if a problem is in NP is a very easy question because all I'm saying is, can you check? If I tell you the solution, can you just check the solution? So this problem is saying, right, so this P versus NP problem is saying, okay, or this question, P versus NP, is saying, take any problem in NP, does it also appear in P? Okay? So it's not like there's one single algorithm to solve everything. That's not what I'm asking, right? You could have a different algorithm for every problem. I'm just saying, like, for every problem where I can check the answer in polynomial time, can I also solve it in polynomial time? That's the problem, yeah.
Did you say the longest path was in NP?
Yeah, so longest path is in the NP. So the way I define the longest path problem is if I give you a graph and a number, right? And I say, okay, is there a path in the graph of total length at least that number, okay? So that's in the NP because how do I check that? Well, if I just tell you what the path is, it's super easy to check, right? I just add up the values in the path, okay? If there happens to be a path, right, of course, that's going to be my hint. If there's no such path in the graph, then I can never come up with a hint, right? When I check it, I'll know, hey, look, this path doesn't add up to, greater than or equal to some number d. Okay. Yeah, essentially every problem we've looked at has always been in NP. Okay. Yeah.
Why would knowing what the answer be useful to us?
Yeah. So why would yeah? So it's not so clear yet, but that's just the way I'm defining this NP set. Okay. It's like if I tell you the answer, you can check it. So that's why this P versus NP question is like surprising, right? Because knowing the solution and checking it just seems way easier than finding the solution in the first place. But surprisingly, we don't know. That's the interesting part, okay? And yeah, and there's going to be yeah, we'll see, okay? It goes a little bit, like there's layers to this. So this is just the first layer, right? We're going to look at one more layer. Yeah, any other questions? What is P, NP? Okay. So why do we care about P versus NP? Well, essentially, right, if we can show that P is not equal to NP, right, ideally the resolution of this will look like, here's a problem, right? Here's a specific computational problem that's an NP. I can check the solution, but I cannot ever hope to find the solution in polynomial time. Then that would be a candidate for a super hard computational problem, right? So essentially, right, if you ever encounter this problem, then you know, like, okay, there's no hope of solving it. So that's why that's one reason we care about this problem, P versus NP. But now we're going to take like a side quest and say, okay, right, like I said, right, if P is not equal to NP, then probably there's a hardest problem in NP, right, like a super hard problem that probably is not in P. So now we're going to take a little detour and say, okay, how do we tell, about the relative difficulty of problems, okay? So now we're going to talk about, like, if I give you two computational problems, like sorting versus max flow, how do I know which problem is harder, okay? And then we're going to tie it back into P versus NP, okay, afterwards. Okay, so now this is a term that we talked about last time, or a couple of classes ago. It's called a reduction. Basically, a reduction between two problems. Let's say from problem A to problem B is just saying that if I have an algorithm for problem B, then I can solve problem A. So basically, right, that is, it's the, think of the word reduction, right? It just means I'm reducing A to a special case of B, okay? So another way to, right, so we write, this is the notation we use, okay? So what this means is, like, B is at least as hard as A. So let me give you a diagram, okay? So we say that A reduces to B if we can take an algorithm that solves B and turn it into an algorithm that solves A, okay? Another way to say that is A is a special case of problem B, right? Because I'm taking an algorithm for B, turning it into an algorithm for problem A. Another way to say is that, right, if I want to say yes or no, right, is an input I a yes instance or a no instance of A? What I can do is I can transform it to an input for B, use the algorithm for B, and then somehow say yes or no for A, okay? So here's a, and this transformation that we do has to run in polynomial time, okay? So here's a quick example, okay? So let's say I have two computational problems, right? Unweighted shortest paths, right? So let's say the problem is I give you two nodes, S and T, and I say, does there exist unweighted shortest path of cost at most 10, right? But let's say I have another problem called weighted shortest path, which is I give you two points in a graph, or two nodes, and the graph can have weights. So clearly, right, that clearly, like, A is a special case of B, because, right, I can take whatever the algorithm is for B and just, like, run it on a graph where I just pretend all the weights are 1, right? So that's why A reduces to B, okay? B is a harder problem than A. All right? Another example, like, let's say that, the problem A is I give you a graph and two nodes, and I say, does there exist a path where if I multiply the edge weights, it's at most some number blah. And I have another problem, right, which is, does there exist a path where the sum of the weights is at most blah? Well, A is a special case of B, right? Because if I have an algorithm to solve B, then I can get an algorithm to solve A by just saying, well, I take my graph, I take my input for A, I take the log of all the values. That's a new input. I plug that into B. B will solve it, and that actually will solve problem A, okay? And there's another example. But essentially, this notation A is less than or equal to B. It's just saying if I have an algorithm for problem B, I can convert it to an algorithm for problem A, okay? Note that it's also possible for A to be reducible to B, and for B to be reducible to A, okay? So we'll see a quick example. Let's consider two problems, right? I give you, okay, these are not decision problems, but just like, just to give an example. Let's say the problem is, I give you n numbers, like sort the numbers. That's problem A. Let's say problem B is find the maximum value in this array. Okay, that's problem B. Well, this second problem is a special case of the first problem, right? Because if I can sort, I can just look at the last index. That's my maximum. But of course, it's also true that sorting is a special case of maximum element finding. If I keep finding the maximum element, right, one at a time, then I can sort, right? Maximum in the whole thing, I can remove the maximum, then remove the second maximum, and so on. Okay. So in this case, both A and B are reducible to each other. Okay, and the main reason for that is I don't really care what the specific running times are. As long as there's like, I can spend polynomial amount of time to go from one problem to the other, then I'm happy. Okay, so that's all this notion is trying to capture. Like, if when I say A is reducible to B, if I have an algorithm for B, can I do some polynomial time, overhead computation and get an algorithm for A? Okay, that's all this means. Okay. Does that make sense? So this is how we quantify which problems are easy and hard. So right, if I know that if I have an algorithm for B, I can convert it to an algorithm for A, then intuitively, right, A is an easier problem than B. Okay. All right. Okay, so now I'm going to define two more classes of problems, okay? And then we'll see something cool, okay? So it turns out, right, I told you there's a set NP, right, which is the set of all problems that are easy to verify, okay? So there's a problem, there's another set, okay, which is called NP hard. And intuitively, these are the hardest problems in NP, okay, intuitively. So what that means is a computation problem is NP hard if every other problem in NP is reducible to A, okay? Meaning if I have a way to solve some problem A, then I can solve every problem in NP, okay? It's not even clear if such problems exist, but I'm just defining this for now, okay? So I'm going to define the set of NP hard. You can think of them as the hardest problems, okay? These are problems that if I could solve, I can solve every other problem in NP, okay? So that's why, previously somebody asked, right, can you use different algorithms? Well, these are the problems where if I could solve any one of these problems, I could solve every other problem in NP, meaning I can solve every problem in P as well, okay? So in some sense, these are like the meta problems, right? These are if I just had an algorithm for this hypothetical problem, I get a problem, I get an algorithm for any problem you care about, which is pretty cool. Okay. Like I said, right, problem is called NP hard if for every other problem in NP, there's a way to reduce this problem to A. Okay. Another way to say it is if I had a hypothetical algorithm for A, I could convert it to a hypothetical algorithm for every other problem in NP. Okay. So these problems are called NP hard. I haven't given you an example of such a problem, right? Which I'll do that in a bit. And well, it's not it's not clear that these NP hard problems should also be in NP. They could be much harder problems. So so we're going to define this class NP complete. And for the rest of the course, you can kind of every problem we'll encounter will actually always be in NP. It's always easy to verify. So in some sense, I didn't have to introduce this NP hard class. I could just totally NP complete. But just for completeness purposes, right? But for your sake, you can just think, right? There's a class P, there's a class NP, and there's a class NP complete. And don't think about NP hard. Just think of there's a class P, right, which is a small class. There's a class NP, which is a big class. And inside NP, there's a core of problems. Okay, these are called NP complete problems, such that every other problem is reducible to these problems. Okay, so if I could solve any problem that's an NP complete problem, I can solve every other problem in NP. Okay. All right. Okay. Yeah, so that's a lot of right. That's a lot of definitions, and as far as you know, right, these sets, let's say NP complete, could just be an empty problem set, right? Maybe there's no problem that's as hard as every other problem in NP. Okay, I'm just telling you, right? NP complete is a set of problems where if I could solve any one of these problems, I could solve every other problem in NP. And you may not, there may not be any such problems. Okay, so as far as this set is empty, but it turns out it's not. But at least does the definition make sense? Like, if it doesn't make sense, this is a good time to ask. Yeah.
So NP complete is that you can solve any problem in NP complete. You can solve all the problems in NP complete.
Yeah.
NP hard is you can solve problem A, you can solve problem X.
No. So right, NP complete. Yeah. So just for your sake, just pretend NP hard doesn't exist. Okay. Just think of the set NP complete. It's a set of problems that are in NP first. Okay. Meaning they're easy to verify. So that's one property. The other property is for every other problem in NP, they're reducible to that problem. Okay. So in some sense, these are the hardest problems in NP, right? So a problem is NP complete if for every other problem in NP, X, let's say, X is reducible to A. Okay. So yeah, I'll have a diagram in a bit, but just think, right? You have this class NP, and inside it you have this core set, right? This hard problems called NP complete. And the idea is if you can solve any one of these problems, you can solve every other problem in NP. Okay, so that's a pretty surprising fact. Like if I have an algorithm to solve any of these problems, I get an algorithm for free to solve any other problem. Yeah.
My question is, this is an intersection. So if it's NP hard, isn't it probably going to be NP also anyways?
So it turns out there are some problems that are harder than all the problems in NP, but they're also not in NP. So it turns out there's much, much harder problems that you can't even verify in polynomial time. But if you could solve them, then you could. Yeah, so it's a little bit weird thing about it. So that's why I'm saying, like, I only introduced it for completeness. Just think about this set NP complete only, okay?
Is there a Venn diagram that goes
Yeah, we're going to see that at the end, the Venn diagram. Yeah, we're going to see that. But just think, right, there's kind of three things that matter. There's a class P, which are polynomial time solver problems, the class NP, which are problems where I can verify in polynomial time, and this class NP complete, which are problems in NP, right? So these are problems where I can verify, but if I had a way to solve them, I can also get a polynomial time algorithm for every other problem in NP. Okay? So if I could, so what this means, right, is like if I had an algorithm for an NP complete problem, I can show P equals NP. Or if I showed for any NP complete problem, oh, this cannot be done in polynomial time, right? Then of course P is not equal to NP. Okay? So these are sort of like the hardest problems that are the barrier. Okay? Okay, so like I said, for the rest of the class, like for the course, we're not going to so much care about these other problems that exist outside of NP. That's not going to matter. Just think of, and I'll actually okay, we're going to skip to the Venn diagram. Okay, so essentially, you can think we're in this part of the world, okay, where P is not equal to P, right? So you have a set P, and you have a set NP, okay, right? P is in NP, right, because something that's easy to solve is easy to verify. And sort of NP complete is like the set of problems that are the hardest problems, okay? If I could solve any one of these problems, then I can solve everything here, okay? And of course, there exist like super hard problems that are just outside NP also. But we're not going to so much worry about these set, okay? Essentially, we're just focused on this circle, okay? And we can pretend for the class like we're in this part of the world, okay? We're going to just kind of always assume P is not equal to NP. Yeah, if P equals to NP, then like some weird stuff happens that we're not going to talk about, okay? Okay. All right. Okay, so right, yeah, so we have three classes, P, NP, NP complete. And as far as you know, right, there's no problem in NP complete so far, right? Because I'm claiming something super surprising, right? I'm claiming if I solve this one problem, then essentially I get a polynomial time algorithm for every problem. Which is like, well, then you don't have, right, the whole class is about like being very clever and smart and like using cool math to come up with algorithms. So I'm saying if you just solve this one problem, you don't have to do any of that. There's actually going to be a way to get a polynomial time algorithm for every problem. So it's like, does there even exist such a problem? Okay. So it turns out, right, right, to even show that, right, we need a problem to start with, right? What is a canonical hard problem that's in NP complete, okay? So it took a long time for people to find such a problem, okay? It took like 20 years, but some people found it, okay? Now that's what we're going to talk about, okay? So in some sense, you can think of this problem. It's called 3-SAT. I'll define what it is, but you can think of it's like the canonical computational problem, okay? It's NP complete, meaning every problem in P, right, or every problem in NP is polynomial time reducible to this problem. Meaning if I could solve this problem, right, if I have a hypothetical algorithm for this problem, I can convert it to an algorithm to solve every other problem, okay? So in some sense, this is like the most important computational problem in some sense, okay? This is at the heart of like NP completeness, okay? So but first, let me describe the problem, okay? So it's a very weird problem. Or it's actually pretty natural, but if you haven't seen something like this, it may not make sense. Okay. So the problem is, right, I give you a bunch of Boolean variables, and I want to set them to true or false, okay? But I have some constraints, and the problem is, can I find an assignment of true and false such that the whole formula evaluates to true? And how does the formula look like? Well, it's going to have clauses, okay? A clause is just like one of these brackets, okay? And each clause will have a variable, a true or false variable. And we're going to have a, so this means an and. Sorry, what am I saying? This means an this means an or. So I want in every clause, there has to be at least one true variable. And this is an and, meaning I want every clause to be satisfied, okay? So it's a weird problem, but it's like saying, can I set these x sub i's true or false, okay? That's the problem. Does there exist some assignment of true or false such that the formula is satisfied? And the formula is satisfied if, right, if every clause has at least one true, right? So that means like, maybe this is a false, maybe this is a true, right? So the whole or would evaluate to true. But this is an and, right? So I want each of these three things to have one true thing in them, okay? All right, so the problem is find and, does there exist a satisfying assignment? Does there exist an assignment of true and false such that the whole thing will evaluate to true, right? So like, right, if I tell you this has n variables, then the naive thing is true then, right? I check all yes, no for every combination. But the question is, right, yeah, does there exist a satisfying assignment? Does it exist an assignment of true and false that turns the whole thing into true, okay? So this is a kind of, feels like a meta problem, but it turns out it's a very flexible problem. Like, as we'll see, many problems are actually 3-SAT in disguise. And turns out it's an NP complete problem. So what that means is, intuitively, any other computational problem that you can think of that's an NP, right? Any graph problem, max flow, sorting, shortest paths, whatever, anything you can come up with, there's a way to convert it into a 3-SAT formula. Okay. So that's the main theory. I mean, we're not going to prove this. Actually, the proof is not very long. So if you're interested, it's on. You can just Google it. But in the 70s, these two people, Cook and Levin, actually, like both of them are still alive, which is pretty cool. Like, seems like a very fundamental thing, but it's not so long ago. I mean, they may not be alive for much longer. They're pretty old, but essentially the thing they showed is like 3-SAT is NP complete. Okay, meaning, right? This is a very surprising statement, right? It's like if I have an algorithm to solve 3-SAT, then every other problem in NP, I can find a polynomial time algorithm. Okay. So if you look at the proof, what it does is it says, okay, take any problem in NP, take a hypothetical algorithm for 3-SAT, I'll convert it to an algorithm for your problem. That's what it does. Okay, that's what the proof has to do. So that's pretty cool. We're not going to prove it in the class, but essentially this is the starting point. Okay, we're going to say, okay, we know in the class, now we know 3-SAT is NP complete. Then we're going to come up with a bunch of other problems, and we're going to show actually these problems are even harder than 3-SAT. They're in NP, so they must be NP complete as well. So then we're going to have a whole bunch of problems that if you solve any one of them, you can solve P versus NP, right? So that's where we're going. But at least does the statement of the problem make sense? Like, what is the 3-SAT problem? It just, SAT stands for satisfiability. 3 stands for the fact that, right, there's 3 variables in every clause. Okay. So actually, maybe it will put this in your homework. But if I have 2SAT, turns out 2SAT is in polynomial time. If I give you a formula where every clause only has 2 variables, you can actually find a satisfying assignment if it exists in polynomial time. But 3 makes it a lot, 3 makes it NP complete. Probably there's no polynomial time algorithm. So that's pretty interesting. What the difference between 2 and 3 is. Mysterious, but at least as a 3SAT problem makes sense. Okay. All right, so what this gives is a starting point to show that other problems are also NP complete, right? If I know this problem is in NP complete, right? What that means is, just again to summarize, take any other problem in NP. I can reduce it to 3SAT, right? 3SAT is a strictly harder problem. But if I show here's another problem that's even harder than 3SAT, it's in NP, so it must be NP complete, okay? And just to make sure you're understanding, right? Can someone tell me why 3SAT is in the NP? Like, what would the verifier do? What is the X that you provide, the hint that you provide to the verifier? Yeah. Yeah, exactly, right? The verifier, what you give the verifier is just the proposed satisfying assignment. And of course, in polynomial time, right, you just run left to right and check, did it satisfy the formula or not? Okay, so that's why 3SAT is NP. And the surprising thing is 3SAT is not only in NP, that's easy, it's also NP complete. That's the hard part. Okay, so now we're gonna talk about other computational problems that are even harder than 3SAT, but they also happen to be in NP. So that will imply that they're also NP complete. Okay, so if you don't like 3SAT, you can instead solve these other problems, and that will also allow you to that will also allow you to get an algorithm for NP. All right. All right. So now we're talking about a graph problem. Okay, so that's like you'll see it's surprising, right? This has nothing to do with graphs. Right? It's just the random Boolean variables, ors and ands. Oops. But we're gonna look at a graph problem, right? Okay, graph problem now. So the graph problem is called the independent set problem. Okay. So the problem is as follows: I give you a graph and a value k, and I want to say, does the graph have an independent set of size at least greater than or equal to k? So what is an independent set? So if I give you a graph, an independent set is a subset of nodes that have no edges in between them. Okay. So here the blue nodes are an independent set because they don't have any edges between them. Okay. All right. So the problem is, right, I give you a graph and a number like 10. Okay. That's the input, or a number like n over 2 even. Okay. And I say, does the graph have an independent set of size at least that value? Can I find that many nodes in the graph that have no edges in between them? Okay. So that's the problem. It's a yes or no question, right? And it turns out 3SAT is reducible to independent set. If I can solve independent set, then I can get an algorithm for 3SAT. Okay, so that's what we're going to show. First, is it clear why independent set is in NP? Why is independent set in NP? Right, it's a yes or no problem. Why is it in NP? What is the verifier? Yeah, somebody else like. Yeah.
I mean, because for this one you can give the blue nodes and check it.
Yeah, exactly. Yeah, exactly. Yeah, exactly. That's it, right? So 90%, 100% of the time, even in this class, the thing to check if a problem is in NP is just if I give the solution, can I check it? Here, right, I'll just tell you this is the claimed independent set of size at least k. I just check there's no edges in between them, right? That's clearly polynomial time. Okay. Now what I want to show is 3SAT is reducible to an independent set, meaning if I have an algorithm for independence. So the way the reductions go is important. That's why the less than or equal to arrow is like useful notation. It's saying if I have an algorithm for independent set, I can solve 3SAT with it. Okay. Okay, so the theorem is 3SAT is NP complete. So how to write? We checked it's in NP. Now we need to show it's NP complete. And the way we do that is say, okay, we're going to take a problem that's known to be NP complete, and we're going to show it's the problem at hand is strictly harder. Okay, because in NP it is harder than this NP complete problem, right? That means it's also NP complete. More formally, right? What did it mean that 3-SAT is NP complete? It meant every other problem is a special case of 3-SAT. But if 3-SAT is a special case of independent SAT, then every other problem is a special case of independent SAT as well. Okay? But the cool thing is, right, we already knew that independent SAT is a special case of 3-SAT. 3-SAT is NP complete. So now we're showing they're actually like equivalent. Okay? Right? Because we know 3-SAT was NP complete, we knew that independent SAT could be reduced to 3-SAT, right? That was the Cook-Levin theorem. But now we're showing the other thing, which is, right, we knew independent SAT is easier than 3-SAT. Now we're showing that 3-SAT is easier than independent SAT. Okay, so in some sense, we're like kind of saying they're equivalent. Okay. So now, right, so what do we need to do? We need to show if I have an algorithm for independent SAT, I can solve 3-SAT. Okay. So first, right, we already checked independent SAT in NP. Right, so yeah, so we want to, like I said, we want to show that if we can solve independent SAT, then we can solve 3-SAT, right? Thus, right, 3-SAT will be reducible to independent SAT, and this will imply independent SAT is NP complete. Okay. All right. So the goal is to reduce 3-SAT to independent SAT. So, right, the word reduce means I'll give you an input to 3-SAT now, right? Right. And I can work with the hypothetical algorithm that solves independent SAT. Okay. So that is something I can work with. That is something I pretend I have. But then I want to convert it to another algorithm that solves 3-SAT. Okay. So then I take. So what that means is, right, take an input to the 3-SAT problem. So let me go back to the diagram for reduction. Right. Right. This B is independent SAT. This A is 3-SAT. I take an input. I have to say yes or no, right? Does the formula have satisfying assignment? I need to transform it to an input that the independent SAT algorithm can understand, right? The independent SAT algorithm can understand graphs, but I have a Boolean formula to start with, so I need to convert it to a graph first. Okay. All right. Right. So what I'm going to do? So what I'm doing is I'm taking an input for 3-SAT. I'm going to convert it to an input for independent SAT. Call my hypothetical independent SAT algorithm. Whatever it returns, I'm going to look at the answer and somehow get a satisfying assignment out of that. Okay. So what that means is I'm going to build a graph based on this 3-SAT formula that has an independent set of size k if and only if there is a satisfying assignment. Okay. So let me just show you the diagram first, and then we can go to the words. So let's say my input to 3-SAT is this, right? I want to say, does this have a satisfying assignment? I want to solve it. I don't know how to solve it, but I do know, right? I do have an independent set solver. So I need to convert it to a graph. So the graph is going to look like this, okay? Essentially, every clause is going to look like a triangle, okay? And across triangles, the way I'm going to connect them is, right, if a clause has some variable x3 and another clause has the opposite of that, I'll have an edge, okay? And, right, if I have 3 clauses, I'm going to say, okay, does this graph have an independent set of size 3? That's going to be my answer. I'm going to ask the independent set algorithm. And intuitively, what's happening is like, right, what is the independent set? I'm not allowed to pick vertices that share an edge, okay? That's what independent set is. So intuitively, right, because I added an edge between all the variables and their complement, I can only pick one of them. So that's the variable, that's the part that's going to be true, okay? Okay? So if I ended up picking this one, then x3 will be false. If I ended up picking this one, x3 will be 2, right? I cannot pick both of them. That would not be an independent set. And also, I need to pick something in, like I cannot pick 2 things in a triangle, right? And if I ask for an independent set of size k, where there's k's the number of clauses, then I have to pick something in every triangle. And that's kind of corresponding to the fact that I'll pick something in every clause to be true. Okay. So now let's go read the math. Okay. So how am I going to turn the clause into the graph? I'm going to create a triangle. But like I said, the nodes in the triangle are going to be corresponding to the variables in every clause. And then across the triangles, I'll add an edge between all the variables and their complements. Okay, so it looks like this. And you can imagine, right, if there was a 4th clause with the x1 not, then I'll have an x1 edge there and this edge here. Okay. And the claim is that if I do this transformation, then this graph has an independent set of size at least k, if and only if this original formula was satisfiable, right? So what that means is if I can prove this, then then that shows that 3SAT is a special case of independent set, right? Because what I'm doing is I'm taking an input to 3SAT, converting it to a graph, asking this independent set algorithm the yes or no question. And my claim is that's going to be the same answer for the clause for the 3SAT problem. Okay. So yeah, another thing to keep in mind is I don't really care what the algorithm for the independent set is doing. That's not the point, right? The point in reduction is just to transform one problem to the other. I don't really care how the algorithms work. I just pretend I have the algorithm, okay? Right? Because I'm not reasoning about the algorithms. I'm just reasoning about the relative comparison between the problems, right? I just want to show that if I could solve one problem, then I could solve the other problem, okay? So now let's quickly prove this claim. This formula is satisfiable if and only if this graph that I constructed has an independent set of size k, where k is the number of clauses, okay? I get to pick k. Well, we have to show two things, right? I mean, it's pretty clear if you think about it, sit there and stare at it for 10 minutes, but I'll just walk you through it, right? Let's do one side, right? If the formula was satisfiable, then there's an independent set, okay? So what do? If the formula is satisfiable, right, that means that at least one of the variables in every clause has to be true, right? That's what it means to be satisfiable. I look at that variable, and I pick that as my independent set, okay? I know there's at least one variable in every clause, okay? So maybe it's maybe x1 should be true, and then x3 should be true, okay? So that makes this one true, this one true, this one true. So then my independent set would be x1, x3, x1, okay? So if there is a satisfying assignment, I found an independent set. I just look at the true variables. Those are my independent set, okay? And and there's not going to be it'll be bad if I pick these three things, right? x3 and x3 bar. But the satisfying assignment is not going to make both of them true, right? Then it wouldn't make sense. So that's why I would never run into this situation, right, where I pick, let's say, both x2 and x2 bar. That won't happen, okay? Right, because either x2 can be true or the complement can be true, right? They both can be true because they're the opposites. So I took a satisfying assignment. I showed you an independent set. Now the other case is if I have an independent set, does that imply a satisfying assignment? And we just go backwards, right? What does it mean to be an independent set? Well, it means, because it's a triangle, I only get to pick one node in every triangle. And because I have these contradiction edges built in, I cannot pick a variable and its complement to be true, okay? So what I do is I look at the independent set, and I just set those things to be true in the formula, okay? I know because I have exactly k triangles, right? And I say the question is, does the graph have an independent set of size at least k? It has to pick one from everything, right? That means there's going to be one variable in every clause that's picked. My claim is that I can set those to be true. That would be a problem, right? If somehow some clause was not satisfied. Well, I picked something in every triangle, so every clause will be satisfied, and I avoided this edge, right? Otherwise, that wouldn't be an independent set. So it's a perfectly reasonable formula assignment to pick. Okay, so that's all this is saying, right? Right. Right. If the graph has an independent set of size k, I just look at the nodes that are picked, and that will be the satisfying assignment. Okay. All right. So it's like a ton of words, but just if we just look at the construction, it's pretty clear what's happening. Okay. Okay. Did that reduction make sense? This formula was satisfying, right? There is a satisfying assignment if and only if this graph had an independent set of size at least number of clauses. Okay. And and the homework and in the maybe final exam, you'll be asked. I'll give you two problems, and you're going to have to reduce from one problem to the other. And essentially, it's going to be okay, I take a problem, I convert it to look like the other problem, and I say the other problem is a yes if and only if the first problem is a yes. Right, so just to summarize what happened, right? Right. I showed you that 3SAT is a special case of independent set because no matter what the 3SAT input is, I can convert it into a corresponding graph. And I asked the graph, like, does the graph have an independent set of size at least k, where k is the number of clauses? And that answer, right, I showed you is a yes, if and only if the clause has a satisfying assignment. So if I have an algorithm for independent set, right, I would convert it to the graph, plug it into the algorithm will say yes or no, and that would be the right answer for the clause. So that means, right, if I have an algorithm for independent set, I convert it into an algorithm for 3SAT. So 3SAT is reducible to independent set. Questions? Yeah.
For this problem, why did you draw them as triangles? Like, why did you not have x1 and x2?
Yeah, so, right. So that's a very good point, right? Yeah, so if you end up having two things in the clause that's true, you can just pick one of them, and that's fine. Yeah, you'll just pick one. Yeah. But the thing to check is like a yes instance. We'll go to a yes instance here, right? If there's a satisfying assignment, right? Maybe x1 and x2 were true. Well, then I just have to pick one. I'd be happy with it, right? If there was a satisfying assignment, then I could convert it to an independent set. Similar, and going backwards, right? If there was an independent set, I could convert it to a satisfying assignment. Yeah, if there was multiple choices, just pick one. Yeah. Good question. Any other questions? So yeah, so for the next like 3 classes, we're going to see lots of examples of reductions. Like we'll have a whole collection of problems that all end up being NP complete. Essentially, the story you'll get is like being NP complete is not a very special thing. There's like hundreds of problems that are known to be NP complete. We don't know how to solve any of them because if we did, right, then you could solve all of them. But yeah, we'll see more and more examples. And yeah, this like reduction may seem a little magical, but you'll get a hang of like, we'll just see so many examples of reductions that, you'll kind of get the hang of like how to convert one problem to the other, right? Like one is a graph problem, one is like a random Boolean problem. I have to get a graph, right? So then you think, okay, I make a graph, but I need to encode the constraint that I cannot pick an edge and I cannot pick a variable and its complement as true. Then that's why I added the edge, You can kind of see the intuition why someone did this, okay? All right, so yeah, let's call it a day here. Yeah, and we'll see more examples.